This video is about time-varying voltage. It corresponds to section 6.3 of Applied Analog Electronics. Now, we have two different sorts of signals that we deal with. Some are constant. These are sometimes referred to as DC signals for direct current. And they're very simple, very easy to describe because they never change. With one number, you can completely describe that signal. It's 3 volts, it's 2 volts, that's it. You're done. For time-varying signals, it's not so simple. We sometimes refer to time-varying signals as AC signals, which is short for alternating current. But for time-varying signals, what do we do? We can't summarize them in just a single number always. So let's take a look at some of the different ways we do describe signals. All right. When we were talking about voltages before, we just used a single symbol, V. So V is the voltage. But for a time-varying signal, it's useful to write it as a function of time. So V of t is voltage as a function of time. And that's sometimes referred to as the waveform. So it's the whole thing. Now, if we're looking at continuous time, that's an infinite amount of information. Not necessarily the easiest thing to deal with. So we often look at summaries of the information. One that we often look at is the average. And mathematically, that would be the integral from some low time to some high time of the voltage with respect to time, and then divide it by the time that we're averaging over. So average, that is sometimes referred to as the DC component of the signal. We're throwing away essentially all the information that's there, that's time varying, and just taking what's the average. And because this is a single number now, we can think of it as being like a DC signal. Now, if we want to summarize the time varying part, something that people often look at is what's called the standard deviation. Which is going to be the square root of the integral of the voltage minus the DC voltage. So we're subtracting off the average, squaring that. And then we want to normalize this by dividing by T high minus T low again. So what this is, it's the square root of the average of the square of the difference from the mean. So this is often referred to as the RMS. That stands for root mean square, because it's square root of the mean, the average, of the square of the difference from the mean. And this is called actually sometimes it's called the AC RMS, because we're looking at just the time-varying portion of the signal. We've subtracted off the average. So it's the same as the notion of standard deviation in statistics, and it's the RMS, the AC component. There is a slight variation of this that gets used, and that is if we take this square root of again a mean, but don't take off the DC, just square the voltage. And again, this is a mean we're taking, so T high minus T low in the denominator. If we take this version, it still looks like a root mean square, but it's not the square now of the deviation from the mean, it is the square just of the raw voltage. This is sometimes called the RMS AC plus DC, because the DC component is still in here. And this one is useful if you're looking at something like, well, how much heat would I get if in a resistor? If I put this time varying signal across a resistor, how much would it heat up the resistor? And what's relevant for that is the average power, and the root mean square voltage gives you a way of computing that average power. And we'll look at that more later on when we look at power, and we'll look at root mean square voltages again when we start looking at, for instance, audio signals. Okay, so we have several different versions of what we can do to summarize the waveform in just a single number. We could say, what's this average value? What's the DC value? What's the RMS value, AC? Or what's the AC plus DC RMS? And voltmeters often measure one or the other of these two, and they're not quite the same thing. So you have to be careful if you've got a voltmeter that's measuring some sort of time varying signal. What is it actually measuring? Make sure you know how to interpret the numbers you get out of your voltmeter. The Teradek data acquisition system reports two numbers. Well, actually, it reports the waveform sampled as frequently as you've set the data acquisition system to do. It reports the average of all the ones that it's recorded, where the T low and T high are the entire recording time. And it also reports the RMS voltage, the AC RMS voltage. And again, this is done over the entire recording time. So you get both the waveform and the two most useful of the summary measurements coming out of the data acquisition system there. Okay, what else might we want to do? There are other ways of looking at this thing, and that is quite often our waveform is going to have something that looks like voltage of time is some DC part plus constant times some function of time, where the function of time is often normalized to be between -1 and 1. So it might be something like a cosine function or a sine function. It can be other things as well. And then if we have this function of time being normalized to being between -1 and 1, then this A is referred to as the amplitude. And the amplitude is a very useful thing because it appears right here in the formula, and so it's an easy one to say, okay, I want to characterize this function. What's its amplitude is very easy to get from the function. Okay, let's take a look actually at a sinusoid, a sine wave or a cosine wave, and see how different measurements here correspond to each other. All right, what I've got here is a signal that's got a 2-volt DC offset, and that DC portion of the signal is often referred to as an offset, sometimes as a bias. So a 2-volt bias or 2-volt offset means that the average is 2 volts. And then I've got plus or minus 1.5 volts from that. So the amplitude is that 1.5 volts. There's another measurement that's often used, and that's the peak-to-peak voltage. And that's twice the amplitude. It's the highest value that we see in the signal minus the lowest value that we see in the signal. And for sine waves and cosine waves, which are nice symmetric signals, that's always just twice the amplitude. Be very careful when somebody says, hey, I've got a 3-volt signal here. What do they mean? Do they mean the amplitude is 3 volts? Do they mean the peak-to-peak voltage is 3 volts? Or do they mean that the RMS voltage is 3 volts? Because the RMS voltage is neither the amplitude nor the peak-to-peak voltage. It's something that you can only measure by essentially doing that integral. Now for sine waves, you can do the integral in closed form analytically and get that that in fact the RMS voltage is square root of 2 over 2 times the amplitude. But that only applies for sinusoids. If you're looking at other signals, you'll get other ratios. And so the relationship between amplitude and RMS voltage is not a fixed one. And there are other properties of the signal we might want to care about besides just how big is it, which is basically all we've been talking about so far. We might want to talk about how fast does it change? That's the frequency of the signal. And we have actually two versions of that to look at, both frequency and angular frequency. So let's go back to the paper here and write down formula for that signal we were just looking at, which was 2 volts plus or minus 1.5 volts. So what we have is that V of t is 2 volts, notice I keep the units around, plus the amplitude, which was 1.5 volts, times, and then I'll have, say, cosine of, and then I've got something here that's time dependent. I'll write it as omega t plus phi. The omega here is called the angular frequency. And it is given in radians per second. We also, however, are often interested in frequency in a different unit, which is full cycles per second, or hertz. So if we want frequency, usually abbreviated F, in hertz, we can write that omega is 2 pi f. The 2 pi is how many radians there are in a full circle. So these two numbers, the angular frequency and the frequency, they carry the same information. They're basically interchangeable, except that you have to be very careful about this factor of 2 pi. And if you're talking about something in hertz, it's always going to be full cycles, because hertz means cycles per second. And if you're talking about angular frequencies, it's always going to be in radians per second. Very, very occasionally you'll see somebody using degrees rather than radians. That just confuses things. Stick with radians and your math will be much simpler. There's one number here I haven't talked about yet. That phi that's sticking out the end there. What is that? Well, this whole thing here that's inside the cosine, the omega t plus phi, that's called the phase. And the phase is something that changes with time. It's what we take the cosine of here. Sometimes people will talk about the phase, though, as just the phase at time 0. So if we stick 0 in here, that's just going to be phi. So sometimes people will refer to phi as the phase, when what they mean is the phase at time 0. And it's another useful property because it sort of tells us, well, where does it start? Where does the signal start? If we go back to looking at that sine wave here, I've not labeled my x-axis here. I don't know when time 0 is. If this is a cosine wave, then that short bar where the amplitude is labeled as 1.5 volts, if that was time 0, then the phase here would be 0 because cosine is 1 at time 0. If, on the other hand, my time 0 was at the 3 volt line there, where I have the peak-to-peak line, well, then my phase is pi or minus pi because I'm a full half a cycle away from the 0 being the maximum. So it's useful to talk about phase sometimes, particularly interesting to talk about phase differences, where you have two different signals that are running at the same frequency, but they're not lined up with each other. How much change there is in time between them is often measured as a phase difference. What's the difference in phase between these two signals? Okay, when we're writing a schematic or a block diagram, it's really useful to label our signals. So if I've got a block diagram that says, okay, I've got a sensor here, I've got some sort of real-world input here, some sort of voltage input here, voltage output coming out of it, I'll want to label this line coming out of the block diagram with how big is that voltage signal? What does it look like? And because sensors often have a DC bias on them, it's very useful to be able to say something like, I'm expecting to see a signal here that is 2 volts plus or minus 1.5 volts. Where the 2 volts here is talking about what's the DC bias, and the plus or minus 1.5 volts is giving me the amplitude of the signal I expect to see. That quick summary of what the signal is really, really useful for determining whether or not your system is working, because you'll later put this into some sort of amplifier, and let's say I'm going to have an amplifier with a gain of 2. Well, if I amplify the DC as well as this, I would expect to see 4 volts plus or minus 3 volts coming out of this thing, because that's what would happen if I amplified this. If it turns out that, hey, that's outside my voltage range, then I know that I can't build this thing. I have to do something different. I have to do something to change the signal, perhaps filter it to get rid of the 2 volt DC bias, something. So being able to put a simple label on every signal makes it much easier to look for consistency across this unit. I can see that this amplifier is doing what it says. It also helps me find errors, and that I can't make this signal if my power supply doesn't go up to those voltages. So always label all your signals with clear labels that tell you what the voltage range is. And here I've done the DC plus or minus amplitude, because that's one of the simplest ones to use. Sometimes you'll label something with an RMS, but then you have to go, well, is there a DC bias or isn't there? And what is the DC bias? So nearly always the simplest thing to do is DC plus or minus amplitude. Okay, that's probably enough for now. We'll be looking a lot more at signals of various sorts, and we'll be revisiting all these concepts over and over again.